are looking at notes for Chapter 1, Section 3. And this is one of my favorite lessons. It's what we're going to talk about is maximums, minimums, increasing, decreasing, intervals, and then even and odd functions. And most of this is super, super important when you get to calculus, if you end up taking calculus. But not only that, it's just a fun pre-cal topic, I think. So we're going to start out with increasing, decreasing, and then minimums and maximums. So I've got kind of a silly example at first, but take a look at this function that's drawn in quadrant 1. What if this function represented a roller coaster? So think about it. If you were on a roller coaster and it looks something kind of like this, here you go, you're on a roller coaster, and I think you know what's happening as you climb this hill. Like, what are you hearing right now? You're hearing click, 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 click. And right here, your heart starts beating really quickly because you know what's getting ready to happen. So, you're up here, you're at the top of the coaster, you hang there for a second, and then here comes the fun part. And then as you're coming down to the bottom here, you know that feeling you get in your chest where like the G-forces are really pulling you down, you feel like your face is all going slack. So right here, we can say that this function is increasing. You would be going up your height would be increasing on the roller coaster. You'd be hearing the click, 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 click. This I'm going to call a maximum because we've reached the peak of the hill of this roller coaster. And then the fun part of the roller coaster is when your height would be decreasing. Or so I'm going to say that the function would be decreasing at this point. And this bottoming out period right here I'm going to call a minimum. And then momentum's going to carry you through. You're increasing. You're going to hear the click, 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 clicking again. So one of the questions I'm going to be asking you while you're looking at a function is, tell me, how about this? First of all, show me where is the function increasing? And you would be able to point it out. You would say it's increasing from here to here. Then it's increasing from here to here. Then it's increasing from here to, is it still going up? Yeah, I think it is a little bit. It's kind of lame, but it's still increasing just a little bit. And then where's the function decreasing? Okay, you could show me, you could point it out. It's going to be decreasing from here to here, decreasing from here to here. All right, but to answer the question, what I really need you to do is tell me where the function's increasing. So you're looking, where are my y values getting higher? You're like, well, here to here. Okay, but tell me the x range when the y's were getting higher. So it's kind of like me saying, okay, roller coaster, you go on and ride the roller coaster. I'll just hang out here. But I'm going to try to watch you the whole way through because, maybe I can't do roller coasters. You go ahead and ride the roller coaster. I'll just hang out here. So you go, you ride the roller coaster. And I'll be like, oh, man, I lost you. I couldn't see where the roller coaster went. That first hill, though. That first hill. When you were going up that first hill, what did you see? And you can say, well, I looked down and I saw the lake. We were above the lake on that first hill. Oh, man. Okay. So when you were coming down that first hill, like where were you in the park? I couldn't see you. Where were? Oh, we were right above the bumper cars. Oh, okay. What about that second hill? That second time that you were increasing. Well, where were you then? I couldn't see you. And you might say, oh, we were right over that ice cream stand that we love to get ice cream at. You're like, oh, okay. And then you might say, and you know what? That second peak that second moment where I knew that it was about to get fun, I looked down and I saw Miss Neal with a really bad sunburn. So I'm going to have you tell me increasing, decreasing, but I'm going to have you look down at your x-axis and say kind of like, well, where was that? Where was the first hill? Where was the second hill? So you're going to kind of like tell me X locations of where all this stuff happened. And then maybe I'll say like, okay, so was it ever lame? Like, was the roller coaster ever kind of lame? And you can be like, yeah, there was where we kind of slowed down and we were just barely kind of going uphill and you knew it was kind of over. And I was like, oh, well, where was that? And you can say, oh, it's right by the carousel. So we're going to look at increasing and decreasing, where it's going up, where it's going down, but you're going to come down here to the x-axis and give me like a location of where the increasing was happening and where the decreasing was happening. Okay, so I've kind of explained about that, and then we are going to look at a relative maximum, which is like a peak in the graph, and a relative minimum, which is like a valley in the graph. And you have to be able to assure me that a max happens when the graph was going up and then switched and went down. Not went up and hung there for a while and then went down. Increasing, click, 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 decreasing. It had to go from one to the other. It couldn't have just stayed constant for a while. By the way, I've been on one of those. I don't know, this may be before your time, but there was a roller coaster at Kings Island. It was called, I think it was King Cobra, where you stood up and you pulled the thing over your shoulders and you were kind of trapped in there, but you stood the whole time on the roller coaster. There's this little seat that you could kind of rest on, and sure enough, it went up the first hill. It was increasing, increasing. You heard the click, 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 and then it stayed there for a while. It stayed there. It actually turned a corner, and then it went down. So that would be, you would not be able to use that when you're looking at a peak or valley. Anyway, relative minimum has to be where the graph was decreasing, and it switched to increasing. Let's see. This is really important. I don't know if it's going to make sense right now, but when I ask you, give me intervals of increasing and intervals of decreasing, you're going to give me X intervals. Again, so I'm going to be asking you, where was the hill? And you're going to look down and say, oh, it was right around where this was. You're going to give me X intervals. And then when I ask for a relative min or a relative max, basically, here's what I'm asking. This would be a relative maximum because we're going to go increasing, switch, decreasing. So this is going to be a relative maximum. When I ask on a graph, what was the relative maximum? I'm asking, how high did it get? And your answer is a Y value. It got this high. I might also ask, where was it? And you're going to have to say, oh, it was right around here. So, relative max, how high did it get? Give me a Y value. Where was it? Give me an X value. Relative minimum, how low did it get? Well, I don't think it got to 0, but tell me a Y value, how low it got, and then I might also ask, where was it? And you're going to give me an X value. So this is what the minimum is, the Y value, and the X is where it happened. Relative maximum, relative minimum. Okay, if that didn't all make sense, you can rewind it and listen to it again, or just wait, because we're going to go over it all again when we start doing examples together. I doubt you're going to have much opportunity to do this in pre-cal or in calculus, but there is a way to find a relative maximum of a function just using your graphing calculators. So, and I've kind of done it for you, even though the steps are all laid out right up there. If you just do those steps, you're going to get the same answer I did. But I typed this in y equals. This is kind of what it looks like. Okay? So it looks like it's increasing and then decreasing. And there is no relative minimum, but there is a relative maximum, and it's a y value. And I found it. I followed those steps, and it was 6.0625. And then for this one, I cleared out my y equals again, typed in this quartic. Here's kind of what it looked like. So just by looking, you should see that these are relative minimums, and this is a relative maximum. And so this is the y value here, and this is the y value here and here, negative 4.5 y value. So on these, we're asked 1, 2, 3, 4, 5, 6, 7, 8. Looks like I'm asking you 8 questions about this one particular graph. So first question, easy question. Give me the zeros. Give me the x-intercepts. Where does it cross the x-axis? And you can tell me, oh, right there. So you say x equals 0. Relative min. So does it ever go down, 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 and then switch and go up, 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 up? No. So there is no relative minimum. Relative maximum. So here's what it's asking. Does the graph ever go up, 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 switch, down, 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 down? Yes, it does. Right here. So, relative max. How high did the graph get? You can say it got to 0. Y was 0. Y was 0. Okay. Where did it happen? Now, when I ask, where did this happen, I want you to look down to the ground, look down to the x-axis. Where were you? So it was at x equals 0. What was the maximum value? 0. That's how high it got. Where was it? It was at x equals 0. We'll do more of those in a minute. Increasing. So here, ready? Roller coaster. Where was it? Where did you hear click, 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 click? Right here. And my interpretation is that this is a parabola, and it goes on forever, so I drew arrows, okay? So click, 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 click. Where was it increasing? Well, where did it start? You can keep looking left, and you can keep looking left, and keep looking left. I think it started way back at negative infinity. This graph was increasing way back at negative infinity. Where did it stop increasing? 0. You know what goes around negative infinity. But at 0, right at the very tip top where your heart's beating really fast, was the roller coaster going up or was it going down? Neither. It was just suspended there for an instant. So don't include 0 as increasing, because right here it wasn't still going up. It wasn't already coming down. It was just kind of neutral. So don't include the 0. And then decreasing, same concept. From 0 to infinity is when it's decreasing. Remember, these are x. These are x values. I know it was decreasing from here on. What was happening along the x-axis when the graph was going down? So from 0 to infinity. And then domain. Easy stuff. Go back like a day or two ago. Domain. How far left does it go? That far. How far right does it go? That far. You know what goes around them. Range. How far left does it go? No. Did not just say that. Range. How low does it go? Well, it keeps going down forever, so negative infinity. How high does it get? It gets to there. Include it? Yes, because there's not this weird, like, open circle drawn there. If you need to, pause it, go over those again, rewind it maybe, the video, and make sure you get it. I'm going to go on to the next one. Okay, Okay, again, my interpretation, this is a quartic, so I think that has arrows. It's going to keep going up and out forever. Zeros, where did it cross the x-axis? Here and here. I wrote it like that. Relative minimum, was it ever going down and then came back up? Yes, it did. How low did it get? It got this low, y equals 0. Where did it happen? Look at the x-axis. Where did it happen? Here and here. Relative maximum. Was the graph ever going up, and then switched to down, 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 down? Yes. Right here. What was the maximum? So how high did it get? It got as high as 16. Where did that happen? Right here, when x equals 0. Okay, increasing. Got to wrap your head around this. So on a roller coaster, and maybe it'll help you to use like highlighters. In fact, I'll use highlighters. I'll use green for increasing. Hope you can see that. When was it increasing? Well, you would hear the click, click, click here, and you would hear the click, click, click here. And the clicking wouldn't stop, and that would be kind of weird. But anyway, so you can see that the graph is increasing from here to here and from here to here. Yeah, I know. Increasing means the y's are getting higher. But look, I'm not asking you what the y's are. I'm asking you, where does that happen? Look at your x-axis. Tell me the x's where I just colored it green. From -2 to 0. -2 to 0. Tell me the x's where I just colored this green. From +2 to infinity. Is it increasing? Like, do you include these? Well, is it increasing at -2? No, you've bottomed out. You're not decreasing when x is -2. You're not increasing when x is -2. You just hung there for a moment before heading up. Decreasing, I'll make it purple. You're decreasing here and here. Decreasing means the y's are getting smaller, but I'm not asking you what the y's are. I'm just asking you, where are the y's getting smaller? Your answer is the x's where that's happening. Where did I just color purple? From -infinity to -2. And where's the other place I colored purple? From 0 to 2. It's like what was happening on the ground when you were coming down the roller coaster. A constant, did it just stay level for a while? No, never did. Domain, how far left, how far right? -infinity, infinity. Range, how low does it get? How high does it get? Domain, left to right. Range, low to high. This is the lowest, highest. One more, and I think you'll really get it here after this one. Zeros happen here and here, -1 and 3. Relative minimum, was it ever going down, 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 and then switch to up, up, up? No. Maximum, was it ever going up, 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 switched down, down, down? No. Constant, did it ever just stay level for a while? Yes, it did. Where? So this is where I'm wanting you to look at the ground, where were you when the roller coaster was lame? It was from 0 to 2. Where was it increasing? Right here. And you're going to give me the x's where it was increasing. It was increasing from negative infinity to 0. Negative infinity to 0. Where was it decreasing? Right here. So look at the ground. Like where were you when the roller coaster was going down? You can say, oh, I was right. So you're looking at the x-axis. From 2 on is when it was decreasing. Domain, how far left, how far right? Well, it's going to keep going left, it's going to keep going right, so negative infinity to infinity. Range, how low does it go? How high does it go? Well, it keeps going down forever, so that's negative infinity, and it caps out. What's the y where it caps out? It caps out at 1, and we're going to include it. Now, I think I've made a really good argument of why you, when we talk about increasing and decreasing, why do you not include the 0 on increasing? Why do you not include the -2 on decreasing? Because remember, when you're on a roller coaster, at that peak, are you going up, are you going down, or is it neither? It's neither. So we're not including that x value in the going up answer or in the going down answer. Should make sense. This one. Some mathy people could argue, Ms. Neal, I think there should be brackets around that. Because the graph was constant from 0 and including 0. All the way to 2 and including 2. It's a good argument. It's very technical. That's like a technicality. So I tell you what, this one, I'll take either way. I'll take parentheses or brackets. These, however, don't try to change them. Don't try to change those to brackets and argue your way through it. You'll lose. You're going to lose that argument. So what you might want to do is just, anytime you're answering increasing, decreasing, constant, maybe just always keep them parentheses. But if you're a little smarty pants and you want to use the brackets on the constant interval, you can. It's acceptable. All right, and the last thing that I want to talk to you about is still looking at graphs, and I want to look at symmetry and even and odd functions. So let me just talk about symmetry first. We used to talk about x-axis symmetry, but it's really not important, so why waste our time on it? Let's just talk about the ones that are really, really important, which is y-axis symmetry and origin symmetry. So I've drawn a picture of a graph that has y-axis symmetry. Many of you are looking at this and you're like, oh, cubic, I remember that from parent functions during Algebra 2. Awesome. It's okay. You don't need to know what type of function it is. Just look at the picture. So isn't it true that I could take this graph and I could flip it over the y-axis and it would look exactly the same? It's y-axis symmetry. Or, another way to look at it, I could fold it. I could take and fold it along the y-axis, and those two sides would match up. Y-axis symmetry. Pretty easy concept. Origin symmetry, a little bit different. Origin symmetry, there is no flipping, there is no folding, there is rotating. So, I know that I got a little bumpy here, and I didn't mean to, but take a minute and imagine leave the x-axis where it is, leave the y-axis where it is. Just take the blue function and rotate it around the origin. So this is your pivot point. Rotate it around the origin 180 degrees. 180 degrees. What do you get? Same exact graph. Origin symmetry. Rotational symmetry. Should take you back to geometry days. This is fold or flip symmetry. This is rotational symmetry. Y-axis symmetry, origin symmetry. Kind of get used to those. Okay, now, this is where I want you to really understand math. So I really want you to focus, listen to me on what I do for these next few minutes before moving on to the next section. If I lose you somewhere during these next few minutes, rewind and listen to it again. It's that important, okay? All right, so take a look at this graph that has y-axis symmetry. I want you to pick an x, any x. Pick a positive x. Pick an x, any x. If I were to pick this x and plug it into my function, what would I get? I would get a y value, right? I would get this y value. Pick a positive x, any x, plug it into your function, what would you get? You would get a y value. It would be right here. Now, whatever x you picked, pick the negative version of that. So if you picked like 3, I want you to now think of what happens if I chose negative 3. Take negative 3, plug it into your function. What do you get? You get a y value. What y value? Oh my gosh. You get the same y value that you got over here. Right? Plug in positive 3, you get something. I don't know, a y value. Plug in the opposite version, what do you get? The same y value. Huh. Pick a bigger x. Let's pick like something out here. Pick a bigger x, plug it in, what do you get? Something up there. Pick the negative version of that. Plug it in, what do you get? You get the same y value. So it doesn't matter whether you plug in a positive x or a negative x. You get the exact same y value. That's going to come up again later. That happens on when you've got y-axis symmetry. Now, let's do the same thing, but with a graph that has origin symmetry. Ready? Pick an x value. Pick an x, any x. Plug it in. When you pick this positive x value and plug it in, look at what you get. I don't know, some y value. It's negative. Ready? Now, instead of choosing this x value, choose the opposite version of that. So instead of choosing, like, I don't know, positive 3, plug in negative 3. What do you get? Well, you get a y value. What y value? The exact same? No. The exact opposite. So when you plug in the opposite version of x, you get the opposite version of y. Plug in a positive, this is what you get. Plug in a negative, you get the opposite. And it works the same way if you pick a bigger x. So let's pick like, I don't know, 10. Pick 10, plug it in, what do you get? Oh, you get a positive y. Positive 10, positive y. Now, plug in the negative version of that. Plug in negative 10, what do you get? You get the negative version. So, whether you plug in positive x or negative x, your results, your y values, turn out to be the opposite of each other. Super important. Let that sink in. Pause it. Copy it down. Rewind it. Listen to it again. Super important. So, this is the last part of your notes, and I've kind of crossed out the test. I do one test. This is like two different tests. I do one test. I do one thing, and I interpret the results. Instead of, maybe let's try this, maybe let's try that, I try one thing. But because I understand this versus this, I can interpret the results. So here I go. I will tell you that it's highlighted right here. We're going to look at even versus odd functions. So hold on a minute. You're used to the words even and odd referencing numbers. 2, 4, 6, 8, even numbers. 1, 3, 5, 7, odd numbers. Completely different. These are functions. Even function, odd function. Does not mean 2, 4, 6, 8, 1, 3, 5, 7 at all. An even function is this. An even function has y-axis symmetry. Memorize that. An even function has y-axis symmetry. An odd function has origin symmetry. This is what an even function might look like. This is what an odd function might look like. On an even function, when I plug in the positive version or the negative version, it doesn't matter. I get the same y value. That's on an even function. On an odd function, if I plug in a positive, I get an answer. If I plug in the negative, I get its opposite. That's an odd function. Okay? So, now that we've made that correlation, I've got 3 examples down here. Tell me, each function, is it even or odd? Or maybe neither. If it's even, it's going to have y-axis symmetry. If it's odd, it's going to have origin symmetry. Now here's how I do it. Here's my function. This is what f, name of the function, looks like with a positive x plugged in it. Remember how I talked about plug in a positive x, see what you get. Plug in a positive x, see what you get. Plug in a negative x, see what you get. Okay? So I'm showing you what f looks like with a positive x plugged in. I wonder what this function would look like if I plugged in a negative x. Well, let's find out. Everywhere you see an x, plug in the negative version of that. Here's what that looks like. And I'm using negatives, so I use parentheses. So, of course, I put negative x right here. And then before I took it to the 4th power, I put it in parentheses. And before I squared it, I put it in parentheses. Okay, ready? When I, do this math, ready? When I take a negative number and I multiply it by itself 4 times, when I take a negative number and raise it to the 4th power, isn't it the same as taking the positive x and raise it to a 4th power? It is. What about this one? So forget about that for a minute. What about take a negative number and square it? Isn't your result of squaring a negative the same as squaring a positive? So my point is, with this negative raising it to the 4th power, with this negative raising it to the 2nd power, it's the exact same as what's up there. So I end up getting 5. And then the result of doing this is going to be the positive version of that. Okay? Write the minus. What happens here? Well, the result of squaring a negative is you get a positive. So the next thing I write after the minus sign is the positive version of this. Oh, and then there's a plus 10 on the end. Now, this is what you get when you plug in a positive x. This is what you get when you plug in a negative x. Compare them. Compare your results. Compare this result by plugging in a negative x with that result, plugging in a positive x. They are exactly the same. You know what that means? Plug in a negative, plug in a positive, you get the exact same thing. This is the type of function we're looking at. Plug in a negative, plug in a positive, doesn't matter, we get the same result. So what that tells me is that function has y-axis symmetry. That function is an even function. It's an even function. It has y-axis symmetry. I'm going to quickly move on to the next one. If you need to hear all that again, just back it up a little bit and you can go through that problem again. Ready? Next one. Here's a function. This is what f looks like when I plug in a positive x. So think back up to those graphs. Remember, plug in a positive x. I get an answer. That's my answer. What happens when I plug in the negative version of that? What happens when I plug in the negative version of that? Well, here I go. I'm going to plug in the negative version. Ready? Plug in the negative version here, here, and here. Okay. Need you to use your brain a little bit. Ready? Take a negative number and cube it. Like negative 2 times negative 2 times negative 2. Okay? You get whatever it was cubed, but the result of that is negative. See? Up here, we cubed a positive number. We got a positive result. Down here, we cubed a negative number. So I get the same result, but it's negative. I get the cubed version, but overall it's negative. Okay? Minus 4. Wait a minute. What's 4 times a negative x? Wouldn't that be 4 times negative x? Wouldn't that be negative 4x? So this would be minus negative 4x. Right? Minus negative 4x. Compare. If this was my result from plugging in a positive, this is my result from plugging in the negative. Did I get the exact same thing? No. Are they exact opposites? So did every piece of this become its opposite? The first piece did, and the second piece did. They're exact opposites. So doing this and doing this. Gave me opposites. Tells me it's an odd function. It has origin symmetry. Last one. Same process. This is what it looks like with a positive x. Let's plug in a negative x. So here we go. Ready? Plug in a negative x. I've shown you what it looks like. Here I go. I'm going to do the math. This time when I take a negative x and I cube it, negative, positive, this results in a negative, correct? A negative cubed results in a negative. Now times that by 3. What we're going to get the same thing that's up here, 3x cubed, but it's going to be the negative version of that. Next piece, plus. I'll write a plus there, but that's just minus x, isn't it? Minus x minus 1. Okay, compare. Compare this result to up here. Are they exactly the same? No. This piece is different, or term. This term is different. This term is different, but not that one. So they're not exactly the same. They're not perfect opposites. So that means it's not an even function, it's not an odd function, it's just neither. And it said, tell whether the functions are even, odd, or neither. And I've shown you what even looks like, it's when you get the exact same result. I've shown you what odd looks like, perfect opposites. Every term is its opposite, and then neither would be just maybe some are positive, some are negative. They don't completely match. They're not complete opposites, just neither. All right, and that wraps it up for section 3 notes.